Solving systems of linear equations by graphing. Let's talk about some vocabulary before we get started. A system of linear equations consists of two or more linear equations. A solution of a system is an ordered pair that checks in both linear equations. When solving a system, there can be three possible solutions. A consistent system is when two linear equations intersect and the solution set is that point of intersection. In other words, if the two lines cross each other, the point where they cross, that's the solution of the system, and that's called a consistent system. So it would look something like this. The point where these two lines cross, right here, is the solution to the system. An inconsistent system is when two linear equations are parallel and there is no solution set. So when we have something like this, where our two lines are parallel, then they're not crossing, so there's no solution. A dependent system is when the two linear equations are identical and there are an infinite amount of solutions. So in a dependent system, it's the same line on top of each other, so it's kind of hard to draw, but it would look something like this, where the two lines are on top of each other. It's the same line on top of each other. So that means every single point on the line, they're sharing. So there's an infinite number of solutions. Alright, so this first one has one solution. And if they were to ask what type of system it is, it would be consistent. This has no solutions. You could do a 0 with a slash through it. That's called an inconsistent system. And then this has infinitely many solutions. Infinitely many solutions, and that's called a dependent system. Alright, so this says use each graph to determine the solution set for each system. Well, number one is a consistent system because it has a single solution. The solution for the system is the point where the two lines cross. And I realize these are kind of small, but if we look at the point right here where those two lines are crossing, that point, the ordered pair for that point would be -1, 3. So that is the solution to that system. In number 2, the lines are not crossing. That's an inconsistent system. But the solution would be no solution. Then for number 3, it's the same line, and so there's an infinite number of solutions. This is a dependent system, but the solution would be infinitely many solutions. Now let's solve some systems by graphing. Okay, so each system, like we said in the vocabulary, means that there's at least two linear equations. So we just need a graph, and every time we're solving a system by graphing, we should have two separate lines. If I look at the first equation, y is equal to -x minus 1, I think the easiest way to graph this would be by slope-intercept form, because this equation is already in slope-intercept form. And remember, when we use slope-intercept form, we just pull out the slope and the y-intercept. The slope of this line is -1. I'm going to go ahead and put it over 1 because we need a rise and a run. And the y-intercept is -1. So remember, when we're graphing, if we have the slope and the y-intercept, we use the y-intercept first. So I'm going to go on my y-axis down to -1 and put a dot. Then my slope is -1 over 1. So I'm going to go down 1 and to the right 1, down 1 and to the right 1. Or I could do +1 over -1, and I would go up 1 and to the left 1, up 1 and to the left 1. And then I just connect my dots. And here's my line. Let's look at the second equation. Alright, this second equation is not in slope-intercept form, but it would be easy to get it in slope-intercept form. all I would need to do is add 2x to both sides. So that gives me y is equal to 2x plus 5. So the slope of this line is 2, or 2 over 1, and the y-intercept is 5. Alright, so if I put my first dot on the y-axis at 5, I would go 1, 2, 3, 4, 5. And then my slope is 2 over 1, so rise 2 and run 1. Now, when we had a negative slope, like this one, I changed, or I put the negative sign with one of the numbers, not both. Because remember, if I put the negative with both, a negative divided by a negative is positive. Well, here we have a positive slope, and I'm running out of room if I try to keep going up. So if I want to have another point to be able to help me graph my line, I can also graph negative 2 over negative 1, because that's still positive. So if I go back to my y-intercept at 5, if I go down 2 and to the left 1, negative and negative, down 2 and to the left 1, that's still part of the same line. Alright, so I'm going to connect those dots. And doing that, doing the negative over negative until I ran into the other line, that just helped assure me of where those lines cross. Because if you're not very precise when you're graphing lines to solve a system of equations, then if either line is off by just a little bit, they're not going to cross in the right place. So this point right here where they're crossing, that's going to be the solution to my system. So I write my solution. If it's a point, I write it in parentheses as an ordered pair, and this would be negative 2, 1 is the solution to my system. Alright, let's look at this next one. The first equation is not in slope-intercept form. So to get it in slope-intercept form, let me just rewrite it over here. 2x plus y equals 7. To get it in slope-intercept form, I'm going to subtract the x, because y equals mx plus b is slope-intercept form. So that's y is equal to 2x plus 7. So my slope is 2, or 2 over 1, and my y-intercept is 7. Okay, so I'm going to go, I messed that up. Okay, so this was a negative 2x, so that should be negative 2. Alright, so my slope is a negative 2. Okay, alright, so my y-intercept is still 7, so I'll go up 1, 2, 3, 4, 5, 6, 7. And then my slope is negative 2 over 1, so I can go down 2, and to the right 1, down 2, to the right 1. You can do that as many times as you want to, but the more times you do it, the more accurate your line is going to be. So I like to do it many times, especially when I'm trying to find the solution to a system. Because like I said, if either one is off, then your lines are not going to cross in the right spot. So let's see. Make sure. Okay. Alright, so that's my first line. And then for my second line, to get this in slope-intercept form, the y needs to be by itself, so I'm going to divide by 2. So that gives me y is equal to, that's negative 4 over 2, which reduces to negative 2x. Okay, so my slope is negative 2, or negative 2 over 1, and my y-intercept, since I don't see a plus anything, my y-intercept is 0. Alright, so my first dot is going to go on 0. Then I go down 2 and to the right 1. Down 2 and to the right 1. Alright, so then I'm going to connect those points. And if you'll notice, these two lines are parallel. We also know that they're parallel because they have the same slope. Alright, so both of them had a slope of negative 2, or negative 2 over 1. So we know they have the same slant, that's the same slope, so we know that they're not going to cross each other. Okay, so if they don't cross each other, then my solution is no solution, because the solution is where they cross. Okay, here's another one. Now, if I look at this first equation, I could get it in slope-intercept form, or remember there's other ways to graph lines. We can do two t-tables, or we can do Find the intercepts. Well, this one would be really easy to find the intercepts because remember, to find the intercepts, we're making that 0, 0 chart. If I put in 0 for x, if I put in a 0 right here, I'm left with y equals -4. So my y is -4. If I put in a 0 for y, if I put in a 0 right here, that goes away. So x equals -4. I put in a 0 for y, x is -4. So I can just plot those 2 points. If you wanted to get it in slope-intercept form, you could do it that way too. It doesn't matter. All right, so on my y, I go to -4. 1, 2, 3, 4. And on my x, I go to -4. 4. Okay, so I'm going to connect those points. All right, that's my first line. And then for the second equation, let me go ahead and get that in slope-intercept form. Okay, so I'm going to add 2x to both sides. And that gives me -2y equals 2x plus 8. And then I divide every term by -2. So that gives me y equals -x minus 4. Okay, so my slope here is -1 or -1/1. And my y-intercept is -4. So I'm going to go down to -4 and put a dot. And then I rise -1, so I'll go down 1 and then to the right 1. Down 1 and to the right 1. So if you'll notice, this is the same line. Let me straighten it up a little bit. Okay, so it's the same line. So that means every point that's on either of these lines is the same. So that means that there are infinitely many solutions. Infinitely many solutions. Okay? All right. This says determine whether the ordered pairs are a solution to the system of equations. So if we have a point in a system of equations, to determine whether or not the point is a solution, all we have to do is plug that point into both equations, and if it's true in both equations, then it is a solution to the system. Well, remember, in an ordered pair, the first number is the x, the second number is the y. Okay, so in that first equation, I'm going to plug in 5 for x. So instead of x, I'm going to write 5 plus 3 times y. Well, my y is 0 equals 5. Okay, so 3 times 0 is 0, so that's just 5 plus 0, which is 5, equals 5. All right, so that's true. It works in that first equation. But like I said, it has to work in both equations in order for it to be a solution to the system. So in the second equation, 2 times, I'm plugging in 5 for x, plus my y is 0, equals 5. Okay, so that's 10 plus 0, which is just 10, equals 5. Okay, so that doesn't work. So this is not a solution. All right, so now let me try the second ordered pair. Okay, this is my x, this is my y. So if I plug it into the first equation, I'm plugging in 2 for x. 2 plus 3 times 1 equals 5. All right, so that's 2 plus 3 times 1 is 3. And 2 plus 3 is 5. Okay, so it works in the first one. Let's see if it'll work in the second one. 2 times 2 for x plus 1 for y equals 5. All right, so 2 times 2 is 4, and I have 4 plus 1, which is 5. So 5 equals 5. So that did work, so this is a solution. And that's how we check to see if an ordered pair is a solution to the system. It has to work in both equations.